The sound you hear is that of an extremely worn pump bearing. Most mechanics will agree that when a bearing sounds this bad, it'll need to be replaced soon. Although most bearings do wear out eventually, in many cases, a bearing may wear out prematurely, which means that the equipment involved will require maintenance more often than it should. Bearing wear can be attributed to many factors, including improper lubrication or cooling. However, another factor that contributes to premature bearing wear is shaft misalignment. When a motor or other driver is coupled to a piece of rotating equipment, such as a pump, the shafts of both components need to be aligned so that the center line of each shaft is in the same line, similar to what we've illustrated here. When two shafts are misaligned, that is, when their center lines aren't in the same line, excessive vibration and equipment wear can occur. Either of these conditions can lead to premature equipment failure and extra maintenance time. Mechanics like yourself are generally responsible for aligning the shafts of rotating equipment. In order to do the job properly, you'll need to know the tools involved and how alignment procedures are performed, as well as what's actually taking place when shaft misalignment is measured and corrected. And there can be several reasons for performing a shaft alignment. For example, when a driver or piece of driven equipment is removed for repairs, the shafts will have to be aligned after it's reinstalled. Or if excessive vibration is detected in rotating equipment, the alignment may be checked to see if shaft misalignment is causing the vibration. Your facility probably has policies that cover alignment procedures for different situations. However, in this program, we're going to look at some of the aspects of shaft alignment involving equipment that has been reinstalled, since that's probably the most common reason for an alignment. We'll discuss alignment theory, the different types of misalignment, how they're measured, and how they're corrected. We'll also discuss what's involved in preparing for an alignment. And finally, we'll look at one method of shaft alignment called the rim and face method. For the remainder of this part of the program, though, let's focus on alignment theory. We'll begin by discussing the different types of misalignment, and we'll use a simple illustration to help you better understand the concepts involved. When two shafts are aligned, their center lines are in the same line, or collinear, as it is commonly referred to. Now, there are two primary types of misalignment: parallel misalignment and angular misalignment. Parallel misalignment means that the two shafts are offset, like the example you see here. If we show the center lines of both shafts, you can see that they are not collinear, but they are parallel. Angular misalignment can be illustrated in a similar fashion. As you can see, they're not collinear. Instead, the center lines intersect at an angle. Now, in addition to there being parallel and angular misalignment, these types of misalignment can be present in a vertical and a horizontal plane. Let's take a moment to illustrate this point. When looking at the end of a shaft, the vertical plane is above and below the shaft. The horizontal plane, on the other hand, is to the right and left of the shaft. In order to see misalignment in the vertical plane, we'll have to look at the shafts from the side. As this side view shows, parallel misalignment in the vertical plane looks like this. The center lines of the shafts are parallel, but not collinear. Angular misalignment in the vertical plane looks like this. The center lines of the shafts are not parallel or collinear, but intersect at an angle. In order to see misalignment in the horizontal plane, we'll have to look at the shafts from a top view. In the horizontal plane, parallel misalignment looks like this, and angular misalignment in the horizontal plane looks like this. In addition to what we've seen so far, it's possible for two shafts to have combined misalignment. That is, a combination of parallel and angular misalignment in both the horizontal and vertical planes. To see this, we'll have to look at the situation from two different views. Here, we're looking at the shafts from the side, so we'll be looking at misalignment in the vertical plane. As you can see, when we extend the center lines, the shafts are parallel misaligned, but there is no angular misalignment. Since we can't determine if there's any misalignment in the horizontal plane from this view, let's look at the same situation from a top view. From this view, we can look at misalignment in the horizontal plane. When we extend the center lines of the shafts, we find that they are angular misaligned. In addition, notice that it is impossible to see the misalignment in the vertical plane from this view. So even though there are two primary types of shaft misalignment, parallel and angular, they can occur in the vertical or horizontal plane or in both, and you'll have to look at both planes to determine the actual misalignment. Well, we've discussed some of the basic aspects of alignment theory. We discussed what shaft alignment is and what it means when two shafts are misaligned. We also saw what parallel and angular misalignment look like in both the vertical and horizontal plane. In the next part of the program, we'll continue with some additional information about alignment theory that you'll need to be familiar with in order to perform an alignment. In the last part of the program, we introduced you to some of the basic concepts of alignment theory. We discussed what it means when we say two shafts are aligned and the different types of misalignment that can be present between two shafts. In this part of the program, we'll use that information to see the basic principles involved in measuring parallel and angular misalignment. Then we'll take a basic look at how shaft misalignment is corrected. A vital part of shaft alignment is establishing reference points and keeping them the same throughout the alignment procedure. If you change your reference points during the alignment, chances are that the shafts wouldn't be aligned when you're done. One reference point you'll need to establish is your orientation in relation to the equipment. There are a few terms we'll need to define in order to explain how it's done. Although you're likely to find many different combinations of drivers and driven equipment, a common situation involves a motor and a pump. So we'll use them as an example in this program. The first two terms we need to define are the movable component and the fixed component. The movable component is defined as the component that will be moved in order to align the shafts of both components. Generally, the movable component is the one that is easier to move. Because pumps are connected to piping that makes them difficult to move, motors are usually chosen as the movable component. The fixed component, then, is the component that is not moved. It remains stationary, and its shaft becomes the reference that is aligned to. Since pumps are generally more difficult to move, they're usually chosen as the fixed component. To properly orient yourself, you should be in a position where the fixed component, in this case the pump, is on your left, and the movable component, in this case the motor, is on your right. Now, because we're concerned with misalignment in both the vertical and horizontal planes, there's another part of this orientation that you'll need to be familiar with. To explain this part, let's look at the hub of the fixed component. As we pointed out earlier, the vertical plane is above and below the shaft, while the horizontal plane is to the right and left of the shaft. If we think of the hub of the fixed component as a clock face, and put on markings for 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock. 12 and 6 o'clock would represent the vertical plane, and 3 and 9 o'clock would represent the horizontal plane. Using this orientation consistently is important in doing an alignment correctly, because it makes keeping track of what the misalignment measurements mean much easier. Now, let's take some time to discuss what's being measured when we measure misalignment. In this illustration, we've exaggerated misalignment in the vertical plane to be able to see it more clearly. By looking at the illustration, you can see that the hub of the movable component is offset towards the 6 o'clock direction. It's this offset that must be measured to determine how much parallel misalignment in the vertical plane exists. You'll also notice that the gap between the two hubs is wider at the 12 o'clock position than at the 6 o'clock position. This difference is what we'll have to measure to determine the amount of angular misalignment in the vertical plane. Now, if we change our vantage point and look at this illustration from the top, you can see that the hub of the movable component is offset towards the 3 o'clock position of the fixed component hub. This offset must be measured to determine how much parallel misalignment there is in the horizontal plane. You can also see that the gap between the hubs is wider at the 3 o'clock position than at the 9 o'clock position. We'll measure this difference to determine the amount of angular misalignment in the horizontal plane. Now, let's take a moment now to look at what's involved in shifting the movable component so that the shafts are in alignment. Correcting for misalignment in the vertical plane involves adding or removing shims under the feet of the movable component. For parallel misalignment in the vertical plane, the same amount of shims will be added or removed under each foot of the movable component. However, when correcting for angular misalignment in the vertical plane, different amounts of shims will have to be added or removed under the feet of the movable component. For example, in this illustration, we'd have to add more shims under the feet at this end than at the other end to correct the angular misalignment. Correcting for parallel misalignment in the horizontal plane involves shifting the movable component in either the 3 or 9 o'clock direction. In this example, the motor must be shifted towards 9 o'clock in order to correct for the parallel misalignment. To correct for angular misalignment in the horizontal plane, the movable component must be shifted in a similar manner. In this example, both ends need to be shifted towards 3 o'clock. However, this end must be moved more than the other end to correct for the angular misalignment. By now, you should have an understanding of the theory behind shaft alignment and the basics of measuring and correcting for parallel and angular misalignment in both the vertical and horizontal planes. In the next part of the program, we'll begin looking at some of the things that must be done before performing a shaft alignment. Before actually performing a shaft alignment, there are some preparations that you should make. During the next 2 parts of this program, we'll discuss these preparations and see how they're performed. Now, not all of these preparations have a direct impact on performing an alignment correctly. However, they're usually included as part of an alignment procedure. One of the first preparations that must be made is to make sure that the pump and motor are isolated and tagged out. Having the equipment start up while you're performing an alignment could seriously injure you. Another preparation involves inspecting the foundation or bed plate that supports the pump and the motor. The foundation should be checked with a bubble level to ensure that it's level. If it isn't, you'll have to verify that the fixed component has been shimmed to make it level. You can check this by placing the bubble level on the shaft or other horizontal surface of the fixed component. If the foundation is concrete or grouted, you'll need to make sure that there are no cracks or loose material that will create an unstable platform for the equipment. It's also a good idea to check the mounting bolts for the equipment. They should be tight, and the bolt anchors should be securely set in the foundation. In addition, the surface of the foundation where the movable component sits should be clean. You'll need to remove any corrosion, paint, or anything else that would interfere with the frame sitting solidly on the foundation. The seating surface should also be stoned to remove any nicks, burrs, or other raised imperfections. Additionally, each foot of the motor should be cleaned and stoned to make sure the motor sits solidly on the foundation. Now, the rest of the preparations we'll be discussing in this part of the program involve dial indicators. So let's take some time to discuss them before we continue with the preparations. There are 2 types of dial indicators typically used for alignment work. The one you see here is called a balanced type. It has a face which is graduated in thousandths of an inch, or mils. It's operated by a plunger or stem that moves the hand on the face. Inward movement of the stem moves the hand in a clockwise or positive direction. Outward movement of the stem moves the hand counterclockwise in a negative direction. You'll also notice that the face can be rotated in order to set the reading to 0 with the stem in any position. This type of dial indicator is used primarily for measuring the misalignment between 2 shafts, which we'll see a little later in the program. The other type of dial indicator used in alignment work is called a continuous type. Its face is also graduated in mils. However, the increments on this one go from 0 to 100 mils. This larger needle indicates stem travel in 1 mil increments between 0 and 100 mils. There's also a smaller needle that indicates stem travel in increments of 100 mils. This arrangement makes it easier to read measurements over 100 mils. Like the balanced type, The face on this dial indicator can be rotated to obtain a zero indication with the stem in any position. You'll notice, however, that the small needle always indicates the amount of stem travel regardless of where the face is zeroed. The next preparation we're going to discuss involves the use of continuous type dial indicators. It's called checking for pipe strain. Pipe strain is the force exerted on the fixed component from suction and discharge piping that is not supported properly. This force, if not corrected, could make it difficult to properly align the shafts. One method of measuring pipe strain involves mounting two dial indicators so that their stems contact the rim of the fixed component's hub. One of the dial indicators is mounted at 12 o'clock and the other is mounted at 3 o'clock. Attaching the dial indicators in this manner allows pipe strain to be measured in the vertical and horizontal plane. Next, each dial indicator is adjusted for a zero reading. At this point, we'll have to loosen the suction and discharge pipe flanges. This will relieve any pipe strain that may have been present. Then the dial indicators are checked. Any reading other than zero on the indicators means that the fixed component moved because of pipe strain. Your facility probably has set limits for the amount of pipe strain that is allowable. In some facilities, the rule of thumb is that any dial indicator reading of more than 2 mils must be corrected. In order to correct pipe strain, adjustments in the piping supports will have to be made. Pipe hangers and supports may have to be moved in order to eliminate pipe strain. Once the adjustments have been made, the procedure we just saw would have to be repeated to see if the pipe strain has been corrected. The next preparation we're going to discuss is checking for a soft foot condition. A soft foot condition exists when one or more of the movable component's feet are in different planes. When this condition is present, the motor housing will twist when the support bolts are torqued down, which can make it difficult to properly align the shafts. To check for a soft foot condition, it's necessary to tighten all of the support bolts on the movable component. Then a dial indicator is mounted to indicate vertical movement of one of the feet and is adjusted to read zero. Next, the support bolt is loosened and the reading on the dial indicator is recorded. Any reading other than zero indicates a soft foot. Most facilities have set limits for the amount of movement that is allowable. In this example, any soft foot condition more than 2 mils must be corrected. To correct a soft foot condition, a shim, the same size as the dial indicator reading, must be inserted under the soft foot. Now the support bolt is retightened and the same steps will have to be repeated for each of the remaining feet. The number of soft feet can vary. In some cases, only 1 foot may be soft. However, it may be necessary to shim 2 or 3 soft feet in some situations. Once all the feet have been checked, it's a good idea to recheck each foot to verify that the soft foot condition has been corrected. Another preparation that should be made is to take run-out readings. This involves measuring the run-out of both the fixed and the movable components. Excessive run-out on either component will make it nearly impossible to correctly align the shafts. If you're not familiar with taking run-out readings, we've included the details on how they're obtained in your text. Although the preparations we've been discussing in this part of the program have focused on either the fixed component or the movable component, some situations may require that these preparations be performed on both components. The methods we've shown here can be used for either component. Let's pause now to give you a chance to review the information that we've talked about in your text. When we continue, we'll look at some additional preparations that should be made before performing an alignment. In the last part of the program, we looked at some of the preparations that are generally made before performing a shaft alignment. We discussed inspecting the foundation, the mounting base, and the motor feet. We also looked at what's involved in checking for pipe strain and soft foot. In this part of the program, we'll continue our discussion on preparing for an alignment. One preparation that's generally made prior to performing a shaft alignment is determining the thermal growth characteristics of both the fixed and the movable components. Thermal growth is a term used to describe the physical movement that occurs as a piece of rotating equipment reaches its normal operating temperature. Different types of rotating equipment have different thermal growth characteristics. For example, when a motor is started up, it produces heat. This heat causes the motor housing to expand, which in turn causes the shaft to rise slightly. On the other hand, a pump that pumps cold liquid has a different thermal growth characteristic. In this situation, the cold liquid passing through the pump causes the pump housing to contract. This then causes the shaft to lower slightly. For that reason, the thermal growth characteristics of both the fixed and the movable components must be determined and taken into account when performing an alignment. Some equipment manufacturers determine the thermal growth characteristics for their products, so you may be able to find this information by checking the equipment manuals for the components you'll be aligning. However, if this information isn't available, it may be necessary to measure the actual thermal growth of the components. Your facility may have procedures on how thermal growth is measured. You'll also find descriptions of a couple of ways of doing it in your text. Up to this point, we've discussed most of the preparations that are made before performing an alignment. The order in which you perform these preparations hasn't been critical so far. However, the last preparation we'll discuss should be the last one done before actually aligning the shafts. It's called setting the face gap of the hubs. Most couplings are designed to operate with a specified amount of space or gap between the faces of the hubs. The purpose of the face gap is to prevent damage to the hubs and coupling from axial movements of the shafts. The term axial movement refers to the amount of movement back and forth that is allowed by the bearings that support the shafts. If the face gap is too narrow, axial movement may cause the two hubs to contact each other and become damaged. On the other hand, if the face gap is too wide, the coupling may separate and be damaged. You'll need to check the coupling manufacturer's specifications to determine the gap that's required for the particular coupling you're using. For example, these specifications show that this hub should have a minimum gap of 1/16 inch, or 62.5 mils. The maximum gap for this hub is 5/32 of an inch, or 156 1/4 mils. You'll also notice that the ideal or normal gap for this hub is 1/8 inch, or 125 mils. With the gap set at 125 mils, the coupling should be able to handle axial movement of the two shafts without damage. In order to set the face gap, the motor must be moved into position. It's a good idea to eyeball the two hubs to get them reasonably close to being aligned while adjusting the coupling face gap. This will make it easier to take misalignment readings later on. Many mechanics will use a straight edge and feeler gauges at this stage to get the two shafts close to proper alignment. Now, you'll need to get a feeler gauge the size of the ideal face gap specification that was determined earlier and insert it between the two hubs. You may have to move the motor to get the face gap set to specifications. Finally, the motor support bolts should be tightened. Setting the face gap for that pump and motor was fairly easy because both components involved bearings that held the shafts in their normal operating position. So axial movement was minimal. However, when larger equipment is involved, particularly components that have sliding surface bearings, much more axial movement may occur. So in those situations, you may have to perform some additional steps before setting the face gap. One step you may have to perform is determining the mechanical center of the fixed component. That is, finding the normal operating position of its shaft. To determine the mechanical center of a pump, this mechanic first forces the pump shaft inward as far as it will go. Then a dial indicator is mounted so that its stem contacts the face of the pump's hub. And the dial indicator is adjusted for a 0 reading. Since the stem was partially compressed when the dial indicator was mounted, the small needle reads 1, meaning 100 mils, when it was zeroed. We'll need to keep this in mind when we take the final reading. Since we need to determine the total amount of axial shaft movement, the next step is to force the shaft outward as far as it will go. Next, the reading on the dial indicator is checked. In this case, the small needle reads 2, meaning that at least 100 mils of travel occurred. The large needle indicates 31.5, so the total travel was 131.5 mils. This reading is the total amount of axial shaft movement. To determine the mechanical center, we'd have to divide the reading by 2, which would be 65 3/4 mils in this example. After the mechanical center is determined, the shaft would have to be moved back inward half the total movement to set the pump shaft on its mechanical center. Then the face gap could be set to the ideal specification. Axial movement is present in motors just like any other piece of rotating equipment. However, because of the magnetic field that is created by the field windings in the motor, the rotor is held in the same position each time the motor is operating. This characteristic is referred to as the motor's magnetic center. Like mechanical center, you may have to determine the magnetic center of the motor before adjusting the coupling face gap. In some cases, the magnetic center for a motor is specified in the manufacturer's manual. However, if this information isn't available, it's possible to determine it while the motor is running. Before determining the magnetic center of a motor, you'll need to ensure that the motor is properly secured to prevent the motor from getting away from you when it's started. Here, the hub and coupling parts have been removed. If this isn't possible, loose coupling parts should be restrained so that they won't fly off when the motor's started. Now the motor can be started. As you can see, there's a great deal of axial movement as the motor comes up to speed. Once it's reached its normal operating speed, its magnetic center can be determined by first spraying the shaft with layout dye. Next, scribe a line on the shaft using the end bell or similar part of the motor as a reference point. When the motor is turned off, and this mark is lined up with the reference point, as it is here, it indicates that the motor shaft is at magnetic center. At that point, the face gap can be set to the ideal specification. For the remainder of the program, we'll be discussing one particular shaft alignment procedure, but you'll need to have a good understanding of the information we've covered up to this point before we continue. So let's pause for now to give you a chance to review this material in your text. Up to this point in the program, we've focused on the theory behind shaft alignment and the preparations that are necessary prior to actually performing an alignment. For the remainder of the program, we're going to be discussing one particular method of shaft alignment. It's called the rim and face method. Chances are that your facility uses this method for at least some of their alignment jobs. The rim and face method involves taking dial indicator readings, using formulas or graphs, and correcting the misalignment in the vertical and horizontal planes. In this part of the program, we'll concentrate on getting everything in order to begin the alignment. Then, in the remainder of the program, we'll look at what's involved in measuring and correcting misalignment using the rim and face method. As we pointed out earlier in the program, two types of misalignment can be present: parallel misalignment and angular misalignment. They can be present in both the vertical and horizontal planes. Parallel misalignment means that the two shafts are offset. Their center lines aren't collinear, but they are parallel. It's this offset that we'll have to measure to determine how much parallel misalignment is present. Angular misalignment means that the center lines of the two shafts intersect at an angle. The gap between the two hubs is larger on one side than on the opposite side. We'll have to measure the difference between the two sides to determine how much angular misalignment is present. To perform an alignment using the rim and face method, a couple of things need to be done. First, we'll need to be able to rotate both shafts. Here, the grid for this coupling has been installed to allow us to rotate both shafts at the same time. Secondly, dial indicators are mounted on brackets, similar to what you see here. In this setup, One bracket is attached to the shaft of the movable component, with two dial indicators mounted at the other end. Another bracket is attached to the shaft of the fixed component. At the other end of this bracket are two areas called targets. As you can see, the stems of the dial indicators are touching the targets. This target will represent the rim of the fixed component's hub. The dial indicator that contacts it will be used to measure parallel misalignment, so we'll refer to it as the P dial indicator. The other target will represent the face of the fixed component's hub. The dial indicator that contacts it will be used to measure angular misalignment, so we'll refer to it as the A dial indicator. In a moment, we'll see how the P and A dial indicators are used to measure the amount of misalignment that is present in both the vertical and the horizontal planes. Now, one thing we'll have to do before measuring misalignment involves determining the amount of deflection in the brackets. Chances are that any dial indicator bracket used for alignment purposes will flex or deflect some small amount while you're using it. In order to obtain accurate dial indicator readings, this deflection, or sag as it's called, must be measured and taken into account when performing an alignment. Some brackets have this information stamped on the bracket. However, if the amount of bar sag isn't known, it will have to be measured before performing the alignment. To do this, the dial indicators and brackets will have to be mounted on a test fixture. But first, you should take a couple of measurements so that brackets can be mounted on the test fixture exactly like they are on the shafts. While the brackets are in place, a tape measure is used to determine the height of the target bracket and the distance between both brackets. Then the measurements are written down. It's also a good idea to mark the shafts along the edges of each bracket so they can be reinstalled in the same place once the amount of bar sag has been determined. The test fixture for measuring bar sag can be an old shaft, a piece of pipe, or a piece of round stock. However, it should be large enough in diameter to prevent flexing that could cause erroneous sag measurements. Here, the dial indicators and brackets have been attached to the fixture, making sure the height and distance between the brackets are the same as they were when mounted on the shafts. With the dial indicators at the 12 o'clock position, the P indicator is adjusted to a 0 reading. It's not necessary to take sag readings on the A dial indicator. The reasons for this are detailed in your text. Now the fixture is rotated to the 6 o'clock position and a reading is taken on the P dial indicator. This reading indicates twice the actual bar sag. The reason for this is that the bar was actually deflected when we had it in the 12 o'clock position. But since we zeroed the dial indicator at that position, we actually negated the sag that was present. So we'll divide the reading by 2 to determine the actual amount of bar sag. In this example, the bar sag is 2 mils. Now, since we'll need to take the amount of bar sag into account when performing the alignment, this value will have to be recorded. Generally, a form called a data sheet is used during alignments to record measurements and other information. This is one example of a data sheet that can be used for the rim and face alignment method. It may not look exactly like the ones used by your company, but chances are it includes similar information. Here, there's space for the equipment's identification, its operating speed, the date, the type of coupling involved, the coupling gap, and the alignment tolerance for both angular and parallel misalignment. We'll be discussing alignment tolerance in more detail later. Here's a space for the bar sag to be entered, so we'll add it. The rest of the form is for dial indicator readings and other measurements that will be discussed as we get further into the alignment procedure. Now the brackets and dial indicators can be reinstalled on the shafts of the equipment to be aligned. You'll need to make sure that they're reinstalled in the same positions. The marks that we made earlier will make that easier. The last thing that needs to be done is to mark the 12, 3, 6, and 9 o'clock positions on the fixed component. These marks will be used to position the dial indicators for taking readings. At this point, we're ready to continue the alignment procedure. Before we go on, though, take some time to review the material that we've just covered in your text. In the last part of the program, we introduced the rim and face alignment method. We saw how bar sag is measured and what a typical data sheet looks like for this method of shaft alignment. In this part of the program, we'll see what's involved in using the rim and face method to measure misalignment in the vertical plane. Measuring misalignment involves taking readings from the dial indicators. Before taking dial indicator readings, though, we'll have to determine certain distances with a tape measure. These measurements are necessary to convert the angular misalignment readings into the actual distance the movable component must be moved to align the shafts. As we take these measurements, we'll record them on the data sheet. Although it's difficult to obtain extremely accurate measurements with a tape, it's usually possible to measure these distances to within 1/8 of an inch. The first tape measurement we'll take is the distance between the center line of the pump shaft and the center line of the A dial indicator's stem. What we need to determine is the swing diameter of the A dial indicator stem. That is, the diameter of the circle through which the A dial indicator travels as we rotate it. So we'll multiply the measurement by 2 and record this value on the data sheet. This value goes here and is labeled D. The next tape measurement we'll take is the distance from the target of the A dial indicator to the center line of the support bolt for the motor foot nearest the hub. This foot is generally referred to as the near foot or inboard foot. As you can see, the dial indicators and brackets have been rotated to about the 6 o'clock position to make it easier to obtain this measurement. Again, we'll record this measurement on the data sheet. It goes here and is labeled X. The final tape measurement is the distance from the target of the A dial indicator to the center line of the support bolt for the motor foot farthest from the hub. This foot is generally referred to as the far foot or outboard foot. This measurement also gets recorded on the data sheet here and is labeled Y. At this point, we're ready to take dial indicator readings. So let's take a moment to establish the proper orientation and then start taking readings. The proper orientation is with the fixed component on the left and the movable component on the right. And if we superimpose a clock face around the fixed component's hub, the 12 o'clock position is on top, 3 o'clock is on the right, 6 o'clock is on the bottom, and 9 o'clock is on the left. Since the brackets are set up in this manner, we'll be using the fixed component's shaft as the reference point. We'll be measuring how much the movable component's shaft is misaligned from this reference point. Since we'll only be measuring misalignment in the vertical plane for now, we'll rotate both shafts so that the brackets are at the 12 o'clock position. We'll use the marks on the pump to make sure we're at exactly 12 o'clock. Next, the face of each dial indicator is rotated so that a reading of 0 is obtained. Now we'll rotate both shafts 1 complete revolution and back to the 12 o'clock position. And we'll need to check the mark on the pump to make sure we're back at exactly 12 o'clock. Then we'll check the dial indicator readings. Both should read exactly 0. The purpose of this step is to make sure that the brackets and dial indicators are securely fastened. If we'd gotten a reading of anything but 0 on either dial indicator, it would have let us know that something had slipped. Since the dial indicators read 0, we can continue. Now, while watching the dial indicators carefully, we'll rotate both shafts until the brackets are at exactly 6 o'clock. In this position, the P dial indicator reads minus 17 mils, and the A dial indicator reads plus 6 mils. We'll need to record these values on the data sheet. As you can see, there are 2 circles here for the initial dial indicator readings. The circle on the left is labeled P. It's for the P dial indicator reading, or parallel misalignment. The box at the top has a 0 written in that represents the 0 reading we set at 12 o'clock. And at the bottom is a box for the 6 o'clock P dial indicator reading. The small area at the left of the box is for the plus or minus sign. So our reading of minus 17 mils would be entered here. The circle on the right is for the A dial indicator reading, or angular misalignment. As before, the 12 o'clock reading has been entered as a 0, and our 6 o'clock reading of plus 6 mils would be entered here. Now, at this point, we've obtained dial indicator readings that can be used to determine parallel and angular misalignment in the vertical plane. However, we'll have to take another set of readings and compare them to the first set. If the readings are the same, we can be certain that we have an accurate set of readings. However, if one or more readings don't match, it indicates that something has slipped, and it'll be necessary to make adjustments and recheck the readings. It's extremely important that any measurement taken when performing a shaft alignment is repeatable. In other words, when you check a measurement for the second time, you should get the same results as the first time. Without repeatable readings, you'll have a difficult time performing an accurate alignment. To complete the alignment procedure for the vertical plane, we'll have to convert our measurements to determine how much the motor must be moved to bring the shafts into alignment. Then we can make the proper moves. And we'll see how that's done in the next part of the program. In the last part of the program, we began discussing the rim and face method of aligning shafts. We'd completed the procedure up to the point where a data sheet had been filled in with dial indicator readings for the vertical plane. The information we obtained tells us the amount of misalignment that is present between the two shafts in the vertical plane. But we still need to determine how this information relates to the actual movement that is required to correct the misalignment. There are a couple of ways to do this, by using formulas or graphs. The use of formulas is covered in your text. In this part of the program, we'll concentrate on how to use graphs to convert the measurements recorded on the data sheet into information that tells us exactly which direction and how much to move the motor in order to correct for misalignment in the vertical plane. Then we'll look at how the actual move is made. The data sheet shows that for this particular situation, the thermal growth characteristics for the fixed and movable components are the same, so we won't have to be concerned with thermal growth in this example. The first thing we need to do, though, is determine the total parallel and angular misalignment in the vertical plane. We'll use information from the data sheet to find the answers. This data sheet is designed to help make the calculations easier. We'll start with the parallel misalignment. The dial indicator reading here is minus 17 mils. If we follow over from the box, we see that we must first divide the reading by 2. That gives us an answer of minus 8.5 mils. Next, we have to subtract the amount of bar sag from this answer. That leaves us with minus 6.5 mils. This value gets written in the box labeled PV and represents the parallel misalignment in the vertical plane. Now, we need to determine the angular misalignment in the vertical plane. Since the A dial indicator reading represents angular misalignment and bar sag isn't a factor for A dial indicator readings, all we have to do is transfer the reading to the box labeled AV. With this information, we can create a graph to determine the move. One nice thing about graphs is that you can see the correction that's needed. To create the graph, you'll need a piece of graph paper. Now we'll need a point of reference, which we'll call the base point. It should be located on the far left side of the graph. Next, we'll draw a straight line from the base point to the right side of the graph. We'll call this line the baseline. Now, the horizontal graduations on the graph will represent increments of 1 inch. The vertical graduations will represent increments of 1 mil, or 1/1000th of an inch. We're going to need some of the information from the data sheet to finish the graph. First, we'll need the value of D, which is the swing diameter of the A dial indicator stem. In this example, D is 10 inches. To plot D on the graph, we'll start at the base point and move along the baseline the value of D. In this case, we move 10 increments. We'll make a point here. This point will be labeled D. Now we'll need the value of X, which is the distance between the target of the A dial indicator and the center line of the support bolt for the inboard motor foot. In this case, X is 12 inches. To plot this point, we'll move along the baseline from point D 12 increments, and we'll make a point here that will be labeled X. Next, we need the value of Y, which is 24 inches in this example. If you recall, Y is the distance between the target of the A dial indicator and the center line of the support bolt for the outboard motor foot. We'll move from point D along the baseline 24 increments and make a point labeled Y. The next value we'll need from the data sheet is the value of AV. In this case, the value is plus 6 mils. To plot point AV on the graph, we must start at the base point. Now, if AV is a positive value, we move up from the base point the value of AV. If AV is negative, we move down from the base point the value of AV. Since AV is positive in this example, we'll move up 6 increments and place a point labeled AV. Now, starting at point AV, we'll draw a straight line that intersects point D. At this point, the graph shows us the relationship between the angular misalignment in the vertical plane and the desired alignment of the shafts. This line, which we'll call the reference line, represents the angular misalignment in the vertical plane. The baseline, then, represents the position the movable component must be moved to in order to eliminate angular misalignment. What we need to do now is factor in the parallel misalignment that's present. Starting at point X on the baseline, we'll follow straight down to the reference line and make a point. This point is labeled XA. Now we'll do the same thing with point Y on the baseline. We'll follow straight down to the reference line and make a point. This point will be labeled YA. Now we need to add the information for parallel misalignment in the vertical plane. To do that, we'll need the value of PV from the data sheet. In this example, PV has a value of minus 6.5 mils. To plot this information on the graph, we need to start at point XA. Now, if the value of PV is positive, we move up from point XA the value of PV. However, in this case, PV has a negative value, so we'll have to move down from the point XA the value of PV, which is 6.5 mils. We'll make a point here labeled XAP. Now we'll do the same thing at point YA. We'll move down the value of PV, which is 6.5 mils, and make a point labeled YAP. Next, we'll draw a dashed line that intersects both points XAP and YAP. This line, then, represents the combined angular and parallel misalignment in the vertical plane. To determine the amount the motor needs to be moved in order to bring the shafts into alignment in the vertical plane, we'll need to do a couple of things. The first thing we need to do is check whether the dashed line is above or below the baseline. If it's below the baseline, as it is here, we have to move the motor up. That means adding shims under the motor feet. If the dashed line were above the baseline, we would have to lower the motor. That would involve removing shims from the motor feet. The second thing we need to do is count the increments between points X and XAP and between points Y and YAP. In this example, the distance between point X and point XAP is greater than 13.5 mils, but less than 14 mils. Because you generally won't be dealing with shims less than 1 mil, it's acceptable to round these values. So in this case, we can round off the value to 14 mils. If we count the increments between point Y and point YAP, we find that the distance is greater than 20.5 mils, but less than 21 mils. So we can round this value to 21 mils. So in this example, raising the inboard feet 14 mils and the outboard feet 21 mils will correct for both angular and parallel misalignment in the vertical plane. Well, we've seen how a graph can be plotted and used to determine how to correct for misalignment in the vertical plane. Now let's take some time to discuss how the actual move is made. Correcting for misalignment in the vertical plane involves adding or removing shims under the feet of the movable component. The graph we just prepared indicates that to correct for the vertical misalignment, we'll have to add 14 mils to the inboard feet and add 21 mils to the outboard feet. One thing you'll need to remember about shims is that as the number of shims increases, it becomes more likely that the shim pack may flex or shift. If that occurs, the shafts may become misaligned when the equipment is operated. For that reason, it's generally recommended that shim packs be limited to no more than 3 or 4 shims. Once the proper sized shim packs are obtained, the support bolts can be loosened and the shim packs installed. You'll notice that the mechanic is using a pry bar to raise each foot enough to insert the shim pack. If the movable component had been bigger, hydraulic jacks might have been needed to lift the foot high enough. Once all of the shim packs are in place, the mechanic retightens the support bolts. In this part of the program, we've discussed how to use a graph to determine the amount of movement needed to correct for misalignment in the vertical plane and how the actual move is made. In the next part of the program, we'll look at how misalignment in the horizontal plane is measured, graphed, and corrected using the rim and face method. Up to this point, we've seen what's involved in using the rim and face method to measure, graph, and correct for misalignment in the vertical plane. In this part of the program, we're going to do the same thing for the horizontal plane. So let's get started. Since we're dealing with the horizontal plane, we'll first have to rotate both shafts so that the brackets are at the 3 o'clock position. And like before, we'll use the marks on the pump to make sure we're at the exact position. Next, the face of each dial indicator is rotated so that a reading of 0 is obtained. Then, the shafts are rotated a full 360 degrees back to the 3 o'clock position to make sure the brackets and dial indicators are securely fastened. Both indicators read 0, so everything seems to be in order. Now, while watching the indicators, the shafts are rotated to the 9 o'clock position and readings are taken on both dial indicators. In this position, the P dial indicator reads +8 mils and the A dial indicator reads -5 mils. We'll record these values on the data sheet. As you can see, there is another set of boxes for the horizontal plane readings. The P dial indicator reading gets written down here next to the circle labeled P. The A dial indicator reading is recorded here next to the circle labeled A. Like before, zeros are entered into the boxes at the 3 o'clock position because we set the dial indicators to 0 at that position. When measuring misalignment in the horizontal plane, bar sag isn't a factor, so we'll only have to divide the P reading by 2 to determine the parallel misalignment in the horizontal plane. The answer gets written in the box labeled PH. And like before, the A dial indicator reading represents the angular misalignment, so its value gets transferred to the box labeled AH. Now we have to take another set of readings to make sure that our initial readings were accurate. We get the same readings this time as well, so everything still looks good. The next thing we have to do is prepare the graph. Basically, it's the same as the one we saw earlier, only this time we'll be graphing horizontal instead of vertical misalignment. We start by plotting the base point, then draw in the baseline. And we'll need the values of D, X, and Y just as before. Now we'll plot these values on the baseline. D has a value of 10 inches, so starting at the base point, we move over 10 increments and place a point labeled D. X has a value of 12 inches, so we start at point D and count over 12 increments and make a point labeled X. Then we do the same thing with Y, which has a value of 24 inches. We move over 24 increments from point D and place a point labeled Y. Since we're graphing misalignment in the horizontal plane, we'll need the value of AH next. In this example, AH has a value of -5 mils. To plot point AH on the graph, we start at the base point. If AH is a positive value, we move up from the base point the value of AH. But since AH has a value of -5 mils in this example, we'll have to move down from the base point 5 increments and make a point labeled AH. Next, we need to establish the reference line. To do that, we draw a straight line from point AH that intersects point D. Now, starting at point X on the baseline, we move straight up to the reference line and make a point labeled XA. And we do the same thing from point Y on the baseline. We'll move straight up to the reference line and make a point labeled YA. Next, we need the value of pH from the data sheet. In this example, it has a value of plus 4 mils. Starting at point XA, we'll have to move up or down to plot the parallel misalignment information. Like before, if pH has a negative value, we move down from point XA. In this example, pH has a value of plus 4 mils, so we'll move up from point XA 4 increments and place a point labeled XAP. Now we'll do the same thing from point YA. We'll move up 4 increments and make a point labeled YAP. Then we'll draw in a dashed line that intersects points XAP and YAP. This line represents the combined angular and parallel misalignment in the horizontal plane. The baseline represents the position we'll have to move the movable component to in order to bring the shafts into alignment. To determine how much to move the motor in order to bring the shafts into horizontal alignment, simply count the increments between points X and XAP and between points Y and YAP. One thing to remember here is how to determine which direction to move the motor. When graphing misalignment in the horizontal plane, if the dashed line is above the baseline, as it is here, you move the motor towards 9 o'clock. If the dashed line is below the baseline, you move the motor towards the 3 o'clock position. At this point, the motor can be moved to correct for misalignment in the horizontal plane. Let's see how this is done. In order to correct for misalignment in the horizontal plane, the mechanic is mounting dial indicators on both an inboard foot and an outboard foot. This will enable him to determine when the proper amount of movement has been made. Once the dial indicators are securely mounted, each one is adjusted for the amount of movement that is required. In this case, the inboard dial indicator is set to 10 mils, and the outboard dial indicator is set to 16 mils. Then the support bolts are loosened. Once the movable component is loose, the mechanic begins making the move. In this example, he's using jacking bolts to move the motor. At the same time, he's watching the dial indicators. When the dial indicators read 0, the move has been completed. Now the mechanic is retightening each support bolt. As he tightens each bolt, he's checking the dial indicators to make sure that the motor doesn't shift. Once all of the support bolts have been properly tightened, the shafts of both components should be aligned properly. However, the mechanic will take another set of dial indicator readings to verify that the alignment is within tolerances specified for the equipment. Data sheets usually have a place for the final set of readings to be recorded. According to these final readings, the alignment is within specs, so the equipment can be returned to service. It's important to note that because of thermal growth and other factors, the final set of readings you take won't necessarily be 0, but the final readings should indicate that the alignment is within the specified tolerance. By now, you should have a general understanding of alignment theory, what's involved in preparing for an alignment, and how to use the rim and face method to accurately align shafts. If you take the time to fully understand what's been covered in this program and practice the techniques we've discussed, you'll be doing a big part in keeping your facility's rotating equipment running smoothly and efficiently.